Hello and welcome to the third of the three films about ionic compounds. Hopefully you've watched the ones about naming and formulas, and you've watched the introduction that tells us how to spot ionic compounds. This one deals with how the particles are actually arranged in an ionic compound and how that affects its properties. Okay, so hopefully by the end of this film you'll understand what we mean by cations and anions and how they're arranged in an ionic lattice, and you'll also be able to relate the structure of this lattice to the physical properties of ionic substances. And we'll start off by looking at the structure. It's drawn in lots of different ways, but the idea is the same. Here's a lattice of a lithium chloride crystal shown. Okay, they've actually shown the positive ions. The positive ions are always called cations, okay? And the negative ions, they're always called anions. So in this diagram here, they're unspecified. In this one, the cation is the lithium ion, the anion is the chloride ion, and you can see that the anion is bigger than the cation, and that's because it's gained electrons, whereas that one has lost them. Okay, so you can see here again, although they haven't specified which is which, we can assume that the green one, because it's smaller, is the cation. Okay, so they're the key terms we need to be aware of when we're talking about this lattice. This lattice is this regular arrangement of cations and anions, and what we can see is that the cations, so if I just pick one here at the center of this cube, it's surrounded by 6 anions. The number's not important, and depending on the type of crystal you've got, you'll get different numbers around it. But the important thing is here that you've got this alternating arrangement of cations surrounded by anions and anions surrounded by cations. And what these blue lines here are showing is the electrostatic attraction. Oh, I've done it again. I did this in the last film. I accidentally changed the slide. I think that's the button on my pen. But anyway, this is the electrostatic attraction between the oppositely charged ions. So positives attract negatives. This electrostatic attraction between positives and negatives, that is what we refer to as an ionic bond. So that's an important definition to learn. An ionic bond is the electrostatic attraction, cross that out, the electrostatic attraction between oppositely charged ions in an ionic lattice. Okay, so that's what the structure looks like. Let's have a look at how we can explain some of the physical properties of ionic compounds by thinking about that lattice. This time I will deliberately move between slides. I won't be doing it by accident, just because I want to show you the structure again as we're talking about these properties. So first of all, we'll look at conductivity. Okay, major mistake here that people make, so be extra careful with your terminology. Major mistake that people make here is to talk about electrons moving, because they've been thinking about metals conducting electricity using electrons. Ionic compounds do not use electrons to conduct. It's the ions that will conduct. Okay, but those ions are in fixed positions in the solid. So as a solid, it won't conduct. It's an insulator, because the ions are trapped in the lattice. Okay, not anything to do with electrons here. As a liquid, those ions can move around, so this substance will be a conductor as a liquid. Okay, and there's two ways of, I suppose, turning an ionic solid into a liquid. One is by melting it. Okay, the other way is to actually dissolve it in another liquid. So in solution, right, for example in salty water, the sodium and the chloride ions have been dissolved, they've been broken up by the solvent, the water, and because they're able to move around, salty water is a conductor. Pure water isn't, because there aren't any ions in the solution to conduct. Solubility, we'll go into this in more detail when we look at more to do with intermolecular forces, but good enough to say at the moment that all ionic compounds dissolve quite well in water, or at least most of them do. There are exceptions. but that's to do with the forces that form between ions and water molecules. As I say, we'll go into that in more detail later. And importantly, malleability or brittleness. I'm just going to get rid of this writing so I can go back and have a look at that other slide. Now, remember, with metals, they were malleable because I could slide one layer of the metal ions over the other without breaking the bonds because the electrons were free to move. However, if I try and slide this layer of ions across here, then this purple is going to come into contact with this purple. In other words, like charged ions are going to come into contact. Okay? And like charged ions repel each other. So, if I try and change the shape of a substance, it will break. That will mean it's not malleable, but brittle. Okay? And that can be explained once again by saying that when the shape of the structure is changed, oppositely charged ions will come into contact and repel, and that will cause the substance to fracture. That doesn't happen with metals, remember, but it does happen with ionic compounds. So ionic compounds conduct, but only when they're liquids, either molten or in solution. They dissolve well in water as a rule, but not always, and they're not malleable, they're brittle, to do with the fact that their ions repel when they're not in the positions they want to be. Okay, and that's about it for ionic compounds. The next series of films that you watch might be about covalent substances, but I guess it's your choice what you watch next, but that's really the next part of the bonding topic.